Incorporating flame-retardant additives, many plastics can have their flame-retardant properties enhanced by adding specific additives. For example, brominated flame retardants, BFRs, and phosphorus-based flame retardants are commonly used. BFRs work by interfering with the combustion process through a gas phase mechanism. When the material is exposed to a heat source, the brominated compounds release bromine radicals, which can scavenge free radical species involved in the combustion reaction, thereby slowing down or stopping the fire. Phosphorus-based flame retardants, on the other hand, often operate through a condensed phase mechanism. They can promote the formation of a char layer on the surface of the material when it is heated. This char layer acts as a barrier, preventing the transfer of heat and oxygen to the underlying material and thus reducing the flammability. Using intrinsically flame-retardant polymers, some polymers have inherent flame-retardant properties. For instance, polyethylamide, PEI, and polyphenylene sulfide, PPS, are known for their good flame-retardant characteristics. These polymers have a molecular structure that makes them more resistant to ignition and flame spread. They can be used directly in injection molding applications where a high level of flame retardancy is required without the need for extensive additional treatment. Optimize the injection molding process. The melt temperature and injection speed can affect the distribution of flame retardant additives in the molded part. If the melt temperature is too high, it may cause the degradation of flame retardant additives, reducing their effectiveness. Therefore, it is important to control the melt temperature within an appropriate range. A lower injection speed can also help ensure a more uniform distribution of the additives and better incorporation into the polymer matrix, which can enhance the overall flame retardant performance of the molded part. The mold temperature can influence the crystallization and orientation of the polymer during the molding process. For some flame retardant materials, a specific mold temperature can help in improving the flame retardant effect. For example, in the case of some polyamide-based flame retardant materials, a relatively high mold temperature can lead to a more compact molecular structure and better flame retardant performance. Design considerations. The thickness of the injection molded part plays a crucial role in its flammability. Thicker parts generally have a higher heat capacity and can store more energy, which may lead to more severe burning. Designing parts with a more uniform and appropriate thickness can help in improving the flame retardant performance. For example, if possible, avoiding thick sections or providing heat. Dissipating channels in thick parts can reduce the risk of fire. Ventilation and airflow. Incorporating proper ventilation and airflow design in the part or the enclosure made by injection molding can also help to reduce the flammability. When a fire occurs, good ventilation can help to dissipate the heat and combustion products, preventing the build up of flammable gases and reducing the intensity of the fire. For example, in the design of an electrical enclosure, vents can be designed to allow the escape of hot gases and reduce the pressure inside the enclosure during a fire.